Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCA-DET, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. Bender's Decomposition and Bender's Multilevel Partition. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Bender's Partition and Decomposition Framework. In 1962, J. F. Benders published his theory oriented to optimization of large-scale problems. The fundamental idea is the partition of a problem into two subproblems, of reduced complexity based on the division of the variables, like coordination variables and subordinate variables. The solution of the original problem is obtained by the coordinated solution of two complementary subproblems. The coordinator, linked to the coordination variables, and the subproblem, linked to subordinate variables. The subproblem provides information to the coordinator by the dual variables associated with its constraints. The coordinator takes the information from the primary level and incorporates it in the form of hyperplanes, Bender's cuts, limiting the feasibility region for the optimal solution of the coordination variables. The algorithm defined by Benders is convergent and solves the original problem. Through the solution of the coordinator problem, it applies only to linear subproblems. This conference presents the generalization of the Benders theory, BT, for several typical cases, where the multi-level structure of the optimization problem enables the effective utilization of BT. The analyzed cases are: decomposition theory is useful when it is possible to grouping variables subordinated into independent sets to formulate multiple subordinate subproblems. In this case, the variables of coordination are also called coupling variables. Multilevel theory is used when there is a multi-level hierarchical relationship within the variables of the problem, and it is possible, inside to subordinate variables, to select a new set of coordination variables for establish an additional level of partition. Multilevel decomposition theory is the result of the combination of the two previous theories. Then, the modeling of large-scale systems can be defined as the process of dividing a large problem in two or more subproblems, with the aim of reducing the dimension of the problem, since the computational complexity grows exponentially with the dimensionality. In this way, the sum of the complexities of the subproblems plus the overhead must be less than the complexity of the integrated problem. This process is based on two concepts. Partition, associated with the process of dividing a problem on two levels based on a hierarchical relationship in which the superior level acts as a coordinator of the other, and decomposition, associated with the process of dividing a problem of a level in multiple issues, of the same hierarchical level. The previous definitions are used in these conferences, considering that there is not a universal concept for the previous terms. As reference, a typical list of cases, in which it is possible to apply partition and/or decomposition schemes. Investment planning. Usually problems oriented to determine investment plans have a structure in which the investment's variables control the operations variables. Many of investment's variables are binary, and the partition allows to handle two problems with different mathematical characteristics. The coordinator model, a mixed integer programming, MIP or MIMP, and the operations subproblem, a linear programming, or nonlinear programming, based on continuous variables. Multi-sectoral planning. Optimizations models that link various sectors. It is possible to select as coordination variables transfers of goods, services, and resources between sectors, defining the production variables at the level of decomposition subproblems associated to each of the sectors. Multi-area or multi-region planning. When performing optimizations that integrate several areas, it is possible to select transfers of goods, services, and resources between areas as coordination variables, and define at the level of decomposition subproblems associated to operations in each of the area. As an example, an electrical system that interconnects several regions of generation and/or consumption. From the hierarchical standpoint, a sector may be composed of multiple areas. The concept of area may be illogical or physical, since also the area may be associated to regions, teams, market agents, etc. Multi-period planning. Mathematical models that integrate multiple periods. It is possible to select transfers of goods, services, and resources between periods, variations of inventories or stocks, as coordination variables, and define at the level of subproblems the production in each period. Discrete time models always have this possibility. Stochastic optimization, an approach oriented to develop optimization processes that consider the possible scenarios of random variables that affect a system. It is normal to define a set of variables associated with the decisions to be taken regardless of the realizations of the stochastic process. This feature depends on variables associated to the simulated operation, conditioned on a possible scenario. Under this scheme, it is possible to define the coordination variables as those that are independent of the scenarios, and to define in the decomposition level, subproblems associated with each scenario. In this case, normally, all subproblems have the same matrix structure, allowing to design efficient algorithms for the joint solution of all the subproblems. The previous cases may occur in a hierarchical multilevel structure, allowing that in a model may be performed more than one partition, and/or decomposition. The definition of sectors, areas, functions, etc., depends on the most convenient point of view to mathematical modeler. The most important thing about this process is that the two extreme levels, the upper coordinator, and the bottom subproblems, or atoms, are the same regardless of the criteria with which the intermediate levels are assigned. The most important aspect about this process is that the two extreme levels, the upper coordinator, and the bottom subproblems, or atoms, are the same regardless of the criteria with which the intermediate levels are assigned. If you analyze the hierarchical structure that is formed, for a large mathematical problem, under the partition and decomposition schemes, you find total similarity with the structure of the human cortex. The image presents three visions of this similarity. Human neocortical structure, Jeff Hawkins' artificial intelligence structure, and large-scale mathematical programming structure. Everything indicates that the structure and joint functioning of the neocortex and hypothalamus is like the structure of the most advanced optimization algorithms. This strong relationship can serve to deepen the knowledge of the two disciplines, artificial intelligence and mathematical programming. Bender's decomposition theory. To present the theory, only the Bender's cuts for optimality will be considered, making it clear that when the subproblem may be non-feasible, feasibility cuts are required. These cuts can be included, following an approach like the one presented. The basic Bender's matrix structure is the dual-angular one. However, there are many real cases in which the matrix associated with the subordinate variables has a diagonal structure, which allows the variables to be segmented into n-independent groups. Then, the subproblem can be decomposed into n-independent subproblems, or decomposition dimensions, which can be solved in parallel. Examples of decomposition's dimension are periods, business, regions, sector, functions, general entities, and random scenarios. The original problem contains the variables of all systems W and the coordinator variables Y, following Bender's theory, without performing any adjustment. The conventional, standard, case implies include only one cut in the coordinator each time that the subproblem is solved. In this case, the diagonal structure of the subproblem matrix is ignored in the optimization process. Standard decomposition Bender's, or standard Bender's cuts, SBC, corresponds to the methodology proposed by J.F. Bender's, that resolves a single large subproblem that integrates all decomposition's dimensions, W, and generated only one cut in each iteration. When we consider the effect of the diagonal matrix, Y act as a coordination variable, and XW dependent variable, it includes the subscript W associated with the subsystems. When we consider the effect of the diagonal matrix, Y act as a coordination variable, and XW dependent variable, it includes the subscript W associated with the subsystems. The image shows the primal problem of subproblems, DBS-PW, and the dual problem of subproblems, DBS-DW. Decoupled decomposition Bender's, or decoupled Bender's cuts, DBC, corresponds to a variation of BT that solves in each iteration a small subproblem for each decomposition dimension. DBC solves W small problems and generates one decoupled cut for each W. The cuts are coupled in the objective function. There are two equivalent formulations for the decoupled coordinator. DBC1, which handles only estimators QW of the optimal cost of each subproblem, and includes as a sum in the objective function, the aggregate cost of all subproblems. DBC2, which includes the variable Q equal to the sum of the cost of all subproblems, and includes Q in the objective function. DCB2, has the advantage to analyze the optimization process in more detail, then this formulation will be used for another type of analysis. When comparing the two coordinators we have, SBC has fewer constraints, but a denser matrix, the information, amount of data, that the two problems have is exactly the same, but, when you decompose the coupled cut into decoupled cuts, it is replacing the maximum of one sum, by the sum of the maximums, which is a deeper cut. Next, the geometric behavior of the two algorithms is analyzed, in order to intuitively understand the decoupled decomposition process. To do this we will work on the feasible zone of the dual problem of the subproblems, which limits the dual variables pi w. A problem that has two subsystems w, symmetric dual feasible zones, defined by a closed polygon of 6 points, it is considered. Let us assume that the optimal solution of the integral problem is given for the values pi 6,1 in subsystem 1, and pi 3,2 in subsystem 2. The table presents the hypothetical solution of the problem for the coupled case, that is the standard Bender's method. In each iteration, the integrated subproblem will report solutions for the dual variables of the two subsystems. The end of the standard coupled process will occur when the optimal solutions in the two subsystems coincide with the optimal solution of the integrated model, in this case in iteration 6. If the cuts are decoupled, in iteration 2, the two optimal solutions have already been obtained. For subsystem 1, in iteration 1, and for subsystem 2, in iteration 2. And therefore, the solution of the decoupled method would have already been achieved. Clearly, it is not possible that the coupled algorithm may require fewer iterations than the coupled system. Additionally, it is possible that, during the coupled optimization process, the optimal solution for each subsystem is listed more than once. This is useless information, for which you pay a computing time. To the extent that the system is more complex, the difference between the two algorithms will be greater. Another aspect to consider is that the independent subproblems will require much less memory to be solved, which makes this requirement not grow with the number of dimensions of decomposition. This is the case of solving optimal control problem, and/or stochastic optimization, in which the dimensions of decomposition may tend to infinity. The graph presents a benchmark coupled versus decoupled Bender's cuts. In it you can see that the decoupled algorithm is 2.8 times faster to obtain the optimal solution. But if the optimality gap is relaxed to 0.005%, this difference can reach 16 times faster. The results come from an application of unit commitment in the electricity sector. Subproblems of the second level can be solved asynchronously in parallel, since there is no need to synchronize problems by iterating on the coordinator, only when all problems of the second level have been solved. Asynchronously, the coordinator can iterate as each subproblem generates information to incorporate cutting planes. Every time the coordinator generates information, a value of y, if a subproblem is free, it can proceed to incorporate the information, without waiting for the other subproblems to do so. In asynchronous parallel optimization, it can assign as many processors as there are decomposition dimensions, provided availability exists, plus one processor for the coordinator. All processors work all the time, minimizing the idle time of the multi-core computer. Resuming SBC, standard Bender's cuts. It corresponds to the methodology proposed by J.F. Benders that resolves a single subproblem, that integrates the subproblems for all decompositions dimensions, and generated only one cut in each iteration. DBC, decoupled Bender's cuts. It corresponds to a variation of BT that solves in each iteration a small subproblem for each decomposition dimension. DBC solves W problems, and generates one decoupled cut for each period. The cuts are coupled in the objective function of the coordinator model. Bender's decomposition using unified cuts. This methodology can only be applied when the dimensions of decomposition are periods, and/or random scenarios. The white paper Bender's Decomposition Using Unified Cuts formally presents the theory presented here, and more information. UBC, Unified Bender's Cuts. When the mathematical conditions are met, it corresponds to a variation of BT, that solves in each iteration a subset of all subproblems. Solving only one subproblem, UBC generates decoupled cuts for each decomposition dimension, periods and/or random scenarios. The cuts are coupled in the coordinator. In 1995, Velázquez Bermúdez, published in the journal Energética of the National University of Colombia Campus Medellín, the article called Optimización estocástica dinámica multinivel teoría general. In English, Multilevel Dynamic Stochastic Optimization General Theory, in which the theory of multilevel benders presented below is formulated. The white paper, Multilevel Benders Decomposition Theory, presents a revision of the theory presented in 1995. There are problems in which more than one level of coordination can be defined hierarchically. That is, inside of a set of subordinated variables exists a relationship such that some variables may act as coordinators of the others. For ease of presentation of the theory, we'll first analyze a case of 3 levels and subsequently generalize the results to S levels. In the development of this theory, and in the following sections, only considered cuts that are generated for reasons of optimality. Consider the problem P, which can be partitioned into 3 hierarchical levels, where Y corresponds to the general coordination variables, and W and X are coordinate variables by Y. At the same time, W may act as coordinator of X, once is defined the value of Y. The fundamental idea of multilevel partitioning is applying BT. The original problem can be split into 2 subproblems, psi a coordinator in Y, and SPY a subproblem in W and X, depending on Y. The subproblem SPY problem may be divided into 2 Y-dependent subproblems, CWY a second-level coordinator on W, and SP2WY, a subproblem on X, which depends on Y and W. Applying BT, the first-level coordinator model, psi, is obtained, where pi x represents the dual variables vector of the constraints A multiplied by x, plus G multiplied by W, equals B minus Fy. Pi W to the dual variables vector of the constraints GW multiplied by W, equals BW minus FWI. I to the number of cuts that have been generated from the lower level, and K index associated to iterations, or cuts, where Qy is the sum of 2 functions Qxy which estimated the value of the cost of variables x, and Qwi the cost of variables w. Let us consider the coordinator problem, CWY, on W conditioned at a value of y. CWY, which includes the function WWY, that is defined by the solution of an optimization problem. WWY function corresponds to the cost C multiplied by x, as a function of W and Y, defined on the 2 upper levels. Let us consider the primal subproblem, SP1Y, coordinated by Y for x and W, that provides feasible values for pi x and pi W. SP1Y is the same function WWY. The dual of SP1Y is DSP1Y. Considering the matrix structure, since W coordinates x, it is possible to solve SP1Y using BT. The coordinator problem, CWY, and the coordinated problem, SP1Y, are equivalent. Therefore, it can be said that at the intermediate level a coordinating problem of the lower level is solved, which in turn is a subproblem of the higher level. Applying BT, the second-level coordinator model, CWY, is obtained, including the cutting planes, constructed using the dual variables of the third level, represented by lambda n. To deepen the interpretation of the cutting plane that is included in CWY, it is convenient to study the dual dCWY of CWY. Let us consider the final iteration K. This is when all variables correspond to the optimal solution, where theta Kn represents the dual variable of the nth cutting plane that has been generated by SP2WY, until the iteration K, of the third level problem, and itex k the total number of cuts generated by third level until the iteration k. This expression implies that the cuts generated by the subproblem in the second coordinator can be replaced by a single cut, generated based on a subrogation, where the weight of each cut is its associated dual variable. This type of cut will be called subrogate Bender's cut. It is a linear convex combination of the lambda and Lagrange multipliers. Surrogate programming theory. Between 1975 and 1982, Velázquez-Bermúdez developed the primal dual subrogate algorithm, PDS, based on the surrogate programming theory, SPT, developed by Greenberg and Pierscala in the early 70s of the last century. SPT proved that in the solution of an optimization problem a set of constraints can be replaced by one equivalent restriction, generated from a convex combination of restrictions, provided that the weights are collinear with the Lagrange multipliers for each constraint. PDS uses SPT to solve convex nonlinear problems, working on with a dynamic subrogate constraint, moving simultaneously in the primal variables, and in the dual variables of the problem. PDS demonstrates that it is possible to replace a set of constraints with an equivalent constraint, which can be obtained from a linear combination of all constraints, if the weight are collinear with the dual variables associated with each constraint. Based on SPT, the cuts generated by SP2WY may be replaced by an equivalent cut, based on the subrogation of all cuts, where the weights correspond to the dual variables associated with each cut. This occurs every time that CWY gets an optimal point, xy, wy, and returns a vector of dual variables to psi. Surrogate cutting synthesizes the information that has been processed in CWY. This can prevent that the number of cuts coming from the lower level grows unlimitedly, since, whenever an optimization cycle is started in CWY, all generated cuts can be replaced by an equivalent Bender's surrogate cut that preserve the memory of the optimization process. The definition of pi xk is general to calculate, in any Bender's coordinator, the dual variables of the restrictions which are not explicitly considered in it, and which are managed at lower hierarchical levels. The dual variables of these restrictions correspond to the subrogated vector of dual variables of the subproblem. For the coordinator of higher level, they correspond to the dual variables in the solution of the problem. In the original way to implement multilevel theory, each hierarchical level returns to the top level only, when it has obtained the optimal solution to the problem, that is parameterized by the decision vector y, preset at higher levels. This implies that at lower levels nested cycles is performed for the upper levels. But more efficient methods using cross-decomposition concepts and parallel asynchronous optimization should be implemented. An example. The diagram presents the multi-level partition of an optimal electricity dispatch model. At the first level, it is the model that represents the interconnected system operator, ISO, which must decide the movement of energy storages, and the start/stop of units. To make its decisions, ISO must capture information on marginal costs, dual variables, from different sources, and centers of energy consumption. At second level, it is the model of supply, demand of energy, parameterized in the decisions of the ISO. Decisions at this level determine the loads that the power grid must serve. In addition to the decisions of the ISO, at this level it is required to know the marginal costs, or prices, in the different bars of the electrical network. The third level is the electrical network, which must meet the demands of load, discharge, in the different nodes of the power grid. It returns to the upper level the marginal costs in the nodes, so that with this information the decisions at the higher levels are reconsidered. The graph presents a benchmark standard Bender's versus tri-level Bender's. In it you can see that the three-level algorithm for complex problems can become 27,600 times faster. There will be problems that simply cannot be solved, with the standard algorithm, in a reasonable time. The results come from an application of unit commitment in the electricity sector. Bender's general multi-level partition theory. The extension of this multi-level theory for cases in which exists more than two levels of coordination is direct. Each coordinator of a lower level generates a cut to the top-level coordinator, summarizing information based on the subrogated vector of dual variables, and on the lower level it may replace all cuts which so far have been used to generate the optimal partial solution. In the case of S levels, consider the problem P, where Y corresponds to the variables of coordination of first level, level 0, and 11 to the variables of level I. Coordination XS corresponds to the lower level, or primary level. The matrix of P has a triangular structure in blocks. Joining decomposition and multilevel partition theories, we can structure complex multilevel systems under a bottom-up approach. Partitioning and the decomposition of a system can occur in multiple ways, without there being a mathematical reason to select one as the best. The diagram presents a system that can be sorted hierarchically by three alternative criteria: business, regions, and functions. Alternatively, it is possible to choose another hierarchy: regions, business, and functions. It is important to note that in both cases it is met. The last layer, the sensory one, is the same since it corresponds to the atoms of the system. These does not change according to the point of view. The upper layer, the coordinators, is the same. The solution to the optimization problem is the same, since it corresponds to different views of the same problem. These systems are characterized by the set of problem families that they include. Each color represents a type of optimization problem related with a physical installation, and/or a decision level. Multi-level decomposition methodologies, like Bender's, are fundamental in the development of artificial hypothalamus. The artificial hypothalamus can be conceived as multiple algorithms, running permanently and autonomously. Each algorithm represents a part of the system, which is represented by families of algorithms, when in the system exists multiple entities of the same type. The exchange of information does not have to be synchronized, since information is produced as the optimization process is developing. Algorithms may be permanently active, or be triggered by events that require their attention. On the other hand, the storage of data in RAM memory, so as not to lose the memory of historical processing, and use the accumulated knowledge whenever an algorithm is required, forms what is an artificial hippocampus. When constructing the artificial hypothalamus based on multi-level decomposition Bender's, the data stored at the end of each cycle of an algorithm must be the dual variables and the primal variables of the problem. Depending on the methodology that is being used, which constitutes a communications protocol, each algorithm will know what to take from the artificial hippocampus when a new cycle begins. Albert Einstein thought that imagination is the highest form of research. Thank you for your attention.